This is Mrs. O'Neill for AP Chemistry, Chapter 17, Section 4, Solubility Equilibrium, our last K. So let's recap those Ks that we've done so far. So far, we've done regular old K. Those dealt with gas reactions. And remember, those gas reactions were given to us either as a concentration or as a pressure. Then we dealt with Ka, Kb, Kw. Well, what were those? Those were weak acids, weak bases, the guys that were not on the list, and they were connected by Kw of water. Now, what's our solubility constant going to be about? It's going to be about salt solutions. Remember these salts that dissolve in water and form ions. So it's going to be how much ions there is versus the solid that it comes from. So you should have watched that intro lesson on solubility. Again, here's my notes. He talked about solubility being the ability to dissolve. So we're going to dissolve, 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 but at some point those ions, there's going to be too many of them, forcing those ions to make the solid again, forcing that equilibrium to go back to the reactant side. So a nice flow chart as always. He, again, telling you that the reaction is equilibrium, that's solid breaking up into ions. He did a PhET simulation. Again, I strongly suggest maybe going to that PhET simulation and practicing a little bit on your own. Talked about there are so many different salts, and we're going to look at that graph like we did in chapter 13 a while back. And that equilibrium constant is really only dealing with the ions. Why? Because our reactant side is a solid, so that is not part of the equilibrium expression. So again, he's comparing different values, and we want to remember that every single salt has its own solubility and at a certain temperature. So we want to remember that K, even though it's a constant, can change because of temperature. Again, he did another PhET simulation telling you as the KSP is lowered, those ions are coming more and more together, forming more and more solid. So what affects KSP? Again, delta G is something you're going to learn in chapter 19, but there's that heat, right? A temperature can affect K as well as some of these other things when we're dealing with KSP. And he also talked about some applications and why this is useful. So onto your notes packet, your objective is going to learn how to use the solubility product constant to determine to what extent this soluble salt can dissolve in water. So again, so far we've dealt with equilibrium, acids and bases, and same phase, right? Those gases at same phase. But now this is a different phase. It's a solid and aqueous solution. So pause the video, read as you write. And now you should be playing my words, right? So dissolving is an equilibrium because the solid will precipitate as fast as it dissolves. So now we have the solid and the dissolved ions in equilibrium with each other. So if we have a little bit of solid, it all goes to ions, but as we add more and more, we're becoming a saturated solution. And then at some point that we add more solid, there's going to be too many ions. It's going to be super saturated, pushing the equilibrium to the left. So I normally don't play a thing, but this is a nice on the molecular level.
Soluble solid such as silver iodide is placed in water, an equilibrium is established between the ions in the solid and in solution. In this view, the water molecules that solvate the ions are not shown to simplify the illustration. The solubility equilibrium is expressed by the solubility product. The silver and iodide ions are of equal concentration in the solution. When sodium iodide, a soluble salt, is added, the concentration of iodide ion is greatly increased. This means that the product of the silver and iodide concentrations exceeds the solubility product constant. Because the product of the ion concentrations exceeds KSP, additional solid silver iodide forms until the product of the iodide and silver ion concentrations again equals KSP. At equilibrium, when the product of the silver and iodide concentrations equals KSP, the silver ion concentration is much smaller than the iodide concentration. The addition of sodium iodide, which greatly enlarges the concentration of one of the ions in the solubility equilibrium, has reduced the solubility of silver iodide. This reduction in solubility is an example of the common ion effect.
So hopefully that made sense on the molecular level, and again, understanding that common ion. So solubility product constant, right? How much solute can dissolve in a saturated solution? That's the maximum. So if we have less than that maximum, it's unsaturated. If we have more than that maximum, we have a supersaturated solution pushing the equilibrium back to the left. Okay, so why is it called a product constant? Well, because we're only dealing with the product of the ions. Remember that the solid is not part of that equilibrium expression. So let's look at example 1. Can we just come up with a KSP expression? Just like our normal case, it's going to be products over reactants. However, there's really not going to be any reactant because that's the solid, but we do need a balanced chemical equation. So the first thing to understand is that barium sulfate is a strong electrolyte. It's an ionic compound. It is a salt. It's going to break apart into ions, but we need to make sure that we have a balanced reaction. So here it's a 1-to-1. So if we want our KSP expression, again, products over reactants, but we're going to get rid of those reactants, and we need to pay close attention to those coefficients, because those coefficients technically are the exponents. Here it's 1-to-1, so you don't see it. But if we look at example 2, again, writing the KXP expression, now we have calcium phosphate. We need to have that balanced chemical equation. It's going to break up into 3 calcium ions and 2 phosphate ions. So our KSP, again, is not going to include those solids, but we do need to include the coefficients as our exponents. So KSP equals the calcium to the 3rd exponent and phosphate to the 2nd exponent. So it's really going to be important to know that. So can you come up with, first of all, the formula for the A and B here, calcium carbonate and chromium 3 hydroxide? Can you come up with the formula, then the balanced chemical equation, and then the KSP expression? Hopefully you got that for A, and hopefully you got that for B. Again, notice the 3 here because of the 3 hydroxide ions. So solubility. Now, the problem with solubility is that they deal again with a lot of molarity, right? Moles per liter, but we're really not dealing with moles. We're dealing with how many grams we can dissolve. So now we got to be able to go from that molarity concentration to grams per liter. Okay, so this is our graph that I told you about. If we look at this line for sodium nitrate, on the line is equilibrium, right? That's the saturated. Anything below is unsaturated, anything above is supersaturated. And remember, there was a difference between gases and solids. So in our calculations or our converting, well, again, we talked about molarity. Molarity is going to be helpful for concentration, but not really helpful for solubility, because we're always dealing with the amount of stuff we can dissolve in grams. So we're going to use formula mass there. We're going to use our empirical formula or the stoichiometric balanced chemical equation to get from molarity to molar concentrations. And of course, KSP is that solubility equilibrium expression. So let's do again more practice problems. So we're given solid silver chromate, which they give us the formula, very nice. They're giving us the silver ion concentration, but we want to calculate the actual value of KSP. So again, we need a balanced chemical equation. So here's our equation. It is balanced and it's a 2-to-1. And again, we're not going to worry about our solid here. And just know that these are at aqueous. I apologize, I should have put the AQs in there. So our silver concentration is 1.3 times 10 to the 4th. Well, how do we get our chromate? Aha, a little stoichiometry. If we know that we have this much silver, we're going to use stoichiometry from our balanced chemical equation, the 1-to-2 ratio. So we're going to take our value of that silver ion and divide by 2 to get the concentration of our chromate. Now we can put it into our KSP expression. However, again, remember we have that exponent. So we're going to plug and chug our numbers, making sure that we square that 1.3 value and get a KSP of 1.1 times 10 to the negative 12th. Very, very small. And remember, no units. Even though this is a constant, it does not have units. So can you do the same thing for example number 2? Very similar in nature. So a balanced chemical equation, making sure that we understand the ratio between those coefficients and then calculate KSP. So I did this one a little differently where I have the balanced chemical equation and then I put my numbers underneath like I'm doing a stoichiometry problem. So if I have 1.2 times 10 to the negative 3 here, that's how much I have here, even though I'm not really worried about it because of the solid, but I have 2 times that for my fluoride ion. So with that information, KSP, making sure that I square my fluoride ion, put in my numbers, plug and chug, and get that answer, and no units. Now this one's going to be slightly different because it's asking for the solubility of the calcium fluoride ion or the calcium fluoride salt that we're using. They're giving us the value of the KSP. So we're going to need to figure out what that means as far as the ions. Well, we need that ice box now. So here's that ice box. Hopefully this makes sense. This is what we're trying to find, is how much initial calcium fluoride we have. Our change is X, but here our change is 2X. So this is our setup. It's a little different. So KSP equals our 2 ions with the fluoride being squared. So X, 2x squared. All of this equals 4x cubed. Hopefully that makes sense. That's a little bit of algebra. So make sure that you're understanding 2 squared would be 4, but then the 2 from here and the 1 from here for the exponent of x would be 3. So then we have to divide both sides by 4, and then we have to take the cube root, okay, the cube root on both sides, or you can take that value to the 1/3 power. So that's going to be our X value. Well, that X value equals the calcium ion, which also equals the calcium fluoride ion. Why? Very nice. It is a 1-to-1 ratio. If this guy was our X value, then we'd have to play around a little bit more, but it's nice that it's a 1-to-1 ratio. So we want, though, grams per liter. Remember, I was telling you how they're giving us concentration, but we really want to know grams per liter. We want to know that solubility. So we need formula mass for that. We need the formula mass of the calcium fluoride, and now we can solve and get an answer of 1.6 times 10 to the negative 2 grams. So in other words, if this is my KSP, and to have a nice equilibrium, a saturated solution, this is how much I can dissolve at 25 degrees Celsius. So can you do example 4? Again, very, very similar, but can you do this on your own? Fill in that ice box, find your KSP, and then of course use your molar mass to find the solubility of grams per liter. Again, very, very similar, and we have that 2 here, so that is 2x on the bottom. So really it's 4x cubed. Do the same thing as far as solving for it. What's our x? Our x is that change in value, but it's a 1-to-1 ratio. But we really want our grams per liter. So we need that formula mass again, and our answer is 8 times 10 to the negative 2 grams per liter. That's how much we can dissolve for a saturated solution, and it should have given us a temperature, but it didn't in this case. So give it some thought, pause, and see if you can come up with an answer. Hopefully that makes sense. Again, looking at that KSP value. So these are shortcuts for KSP. In other words, if something is broken up into 2 ions, our formula really is going to be KSP x squared. If it breaks up into 3 ions, it's going to be 4x3 or 4x cubed, and so on. So hopefully, if you're looking at this, these are just shortcuts. But if you still like to use that X box, it's going to give you that same information. So again, what is this S? This S is really that X part of our equilibrium expression, or that X box. So hopefully this makes sense as well, what I just talked about. So the S is really the X, and there's those shortcuts or those patterns if you like to do that as well. So that's all, folks, for the different Ks, the different equilibrium constants. See you in class.